all the disciplines are integral disciplines for designing and enhancing energy conversion technologies. For the thermodynamics, which is that is scientific disciplines governing the transformation, exchange and efficiency of the energy from one form to another, and heat transfer, that is science of quantifying, controlling how energy migrate due to temperatures differences is vital in the energy conversion processes. Fluid mechanics, the study of the fluid behavior, pressure dynamics and the flow mechanics will be handled in these energy conversion technologies. And chemical reaction engineering, whether it is the gasification or the combustion, that is the chemical reaction engineering field, directing the design and scaling up the chemical reactions for energy efficient energy transformation and generations. And electrochemistry, the study of electricity, chemical reactions, interplays fundamental for energy storage and conversion technologies. Here this analysis of momentum, heat and the mass transfer will be pivotal for the predicting and optimizing energy system performance, which is the transport phenomena. But thermodynamics will play major role in these energy conversion technologies. Here if you see the another importance of the thermodynamics in the energy and the environment, that is system efficiency and sustainability and environmental impact. Using thermodynamics, one can define and measure the efficiency of the various systems. Example is the calculating the efficiency of heat engine. Again, for maintaining the sustainability of the environment and what is the impact on the environment. This thermodynamic offers insights into how energy conversion can impact the environment, especially regarding entropy and waste heat. This helps in designing processes which are both energy efficient and environmentally friendly. Now, if you see the thermodynamics, that is energy conversion systems, here we can see that that is work done by the pump, which is if from this the output is that is supplied is fed to the boiler where heat is supplied, and from the boiler steam is generated, that is through the turbine we can get the work output, that is then converted to the power, and the vapor can be condensed further and heat will be out. So, this is the simple just Rankine cycle. This thermodynamics energy conversion systems. So, here biogas fueled solid oxide fuel cell, micro CHP combined heat power systems, where the energy is getting that is converted, that is biogas if is supplied, that is produced from the biomass, biogas is supplied to the reformer, and then from where finally we can get the steam, and also we can get the net electric power, and their internal power consumptions whatever will be there, that can be sufficient. This net electric power will from that we can get the net internal power consumption as well as some excess also we can get from that. This is the thermodynamics also from the simplified process flow sheet. It is the for polygeneration systems, and where we are getting carbon dioxide to storage, and carbon dioxide emitted, sulfur emitted, and syngas is produced from this carbon dioxide, sulfur, water we are getting, and there also we are getting the power. The fundamental laws of thermodynamics are applied, that is first law of thermodynamics, where the conservation of the energy principle is there, and first that is one of the most fundamental laws of the nature. Energy can change forms during the interaction. Total energy remains constant. It cannot be created or destroyed. So, first law of thermodynamics again expresses the conservation of the energy principle, asserts that energy is a thermodynamic property. Then conservation of law for the mass, that is mass cannot be created or destroyed. It is a closed system, no mass transfer, mass remains constant. Open systems, that is mass can enter or the leave. And there the energy forms, kinetic potential or the internal energy will be the different type of the energy, where the first law describes conversion between these forms and the energy transport as transported as heat and the work. So, fundamental laws of thermodynamics, that is second law of thermodynamics, is also applicable. That is here in the thermodynamic processes, where the process have inherent restriction. Example, heat flows from the hot to cold, not the vice versa. Second law of thermodynamics, that is introduces entropy, which can be created, not destroyed, and describes the change of energy entropy due to transport and the creation. It also processes with entropy creation which are irreversible, leading to a work loss. Implications of the second law, that is efficiency of the heat engines is restricted to values below 100%, where heat cannot be fully converted into the work. And also quality and the quantity of the energy is determined, that is energy has both quality and quantity. Processes occur in the direction of decreasing energy quality. Example, hot coffee cools down, cool coffee does not heat up by itself. Modeling and analysis of thermodynamic systems, that is some problem systems statements are there with which you can do, and step 2 will be schematic, and step 3, so whatever the assumptions for the modeling, we need some assumptions and approximations, then the governing equations, then the what are the properties, then solution procedure, reasoning, verification, and the discussions. Thermodynamic balance equations, where the systems is considered to which the energy flows and in and flows out across the boundary from the system to surrounding, surrounding to system. Similarly, work is done on the system, that is from surrounding to work input from the surrounding to system, and work output from the system to surrounding. Similarly, it occurs in the closed systems or the control mass. In the open systems or the control volume, here the mass is entered into the control volume systems, where the work transferred across the boundary, that is work from the surrounding, work is done by the surrounding on the systems, and work is also transferred from the system to the surrounding. And similarly, product energy also flows across the boundary from the system to surrounding and surrounding to the system, and some mass is collected out from the system, and that is the open system or the control volume. And here thermodynamic balance equations, that is closed systems, Mi mass input equal to mass F mass output, and means total mass remains constant. So here energy balance, that is will be energy in minus energy out, that will be total energy. So net change, net energy transferred by heat and the work, change in the equal to the energy total energy or the net energy in the internals, that is kinetic energy, internal energy, and the potential energies. So exergy balance, that is net exergy transferred by heat and work, that is x in minus x out minus x destroyed, how much energy or the heat and work gets destroyed, that is x destroyed, equal to the delta x systems, that is change in exergy. Thermodynamics balance equations, that is open systems, mass in minus mass out is the net mass in the systems, and energy balance similarly energy in minus energy out is the net energy in the systems. So, energy transfers by the heat, work and the mass, and the net energy, that is the change in internal kinetic potential, all sorts of the energy existing in the system. Similarly, exergy balance will be x in minus x out minus x destroyed, that is the delta x systems, which is the change in the energy, and this exergy transfer gets done by the heat, work and the mass. See example 1 on the balance equations for this thermodynamics concept. A textile plant requires 4 kg per second of the saturated steam at 2 megapascal, which is extracted from the turbine of a cogeneration plant. Steam enters the turbine at 8 megapascal and 500 degree centigrade at a rate of 11 kg per second and leaves at 20 kilopascal. The extracted steam leaves the process heater as a saturated liquid and mixes with the feed water at constant pressure. The mixture is pumped to the boiler pressure, assuming an isoentropic efficiency 88% for the both the turbine and the pumps. Determine the rate of process heat supply and the net power output. The solution is this: for the problem state, as combined heat and power facility is designed to produce electricity and the process heat. Some steam taken from the turbine at a high pressure, which is used for heating, and the facility's heat output rate, the total net power generated and the plant's efficiency need to be calculated. So, here assumptions: steady operating conditions exist. Second assumption, kinetic and the potential energy changes are negligible. This thermodynamic balance equations, for these solutions, the schematic of the diagram of the system, schematic diagram for the systems is shown here. Here we can see that how the that is heat is process heat is that is transferred, that is to the boiler where heat is supplied, process heat, then it is from this steam generated, that is passed through the turbine. From there heat is it is a combined heat and power. So, steam is generated as well as the electricity is generated. Now, the steam is condensed in the condenser and that heat is it is transferred to the process heater, and then the that is in the condenser, whatever the that is steam will vapor will be condensed, that steam again we can be recycled to through this, because its heat will lot of heat will be there, and from the process heater also we can get the power that also can be fed to the boiler, means for the internal energy consumptions. Next. So, thermodynamic balance equations solutions, that is rate of process heat supply, that is Q process mass into net enthalpy, that is m dot 7 into H7 minus H3, where that is m dot 7 is the m dot 3, that is from the mass balance for the process heater. M dot shows the mass flow rate, and H7 and the H3, the difference is the enthalpy values at stream 7 and stream 3 enthalpy, that is the thermodynamic property. which use steam tables to define the enthalpy values with the two independent properties, and for different substances one can get need to employ various property methods, that is to define their thermodynamic properties. Several commercial tools are also available. By choosing the appropriate property method, one can estimate the thermodynamic properties such as enthalpy, entropy and the specific volume. Now, using turbine isentropic efficiency, one can calculate the enthalpy at the stream 7. So, it is the efficiency that is for the turbine where H6 minus H7 divided by H6 minus H7. So, thus at the pressure 6, that is 8 megapascal, temperature 6 for the 6th stream 500 degree centigrade. So, from this H6, that is enthalpy from the steam table, it can be obtained. So, 3399.5 kilojoule per kg, and here S6, that is 6.7266 kilojoule per kg degree Kelvin. So, for the 7th stream, pressure is 2 megapascal, and S, that is S7 S equal to S6, which is from that again enthalpy for the stream 7, that is 3000.4 kilojoule per kg. Now, for the again enthalpy, that is the H7, which is H6 minus efficiency into H6 minus H76, means side stream of the 7th stream, H7S. So, thus H7 is calculated 3048.3 kilojoule per kg. Now, next step, one should find H3, that is using steam tables. So, where it is H3 equal to HF at 2 megapascal pressure, which is 908.48 kilojoule per kg, assuming no pressure drop for the process heater. Now, Q for the process heat transfer for the process m.7 H7 minus H3, which is calculated, that is 8559 kilowatt. Now, the power output, which is W dot net, which is turbine work done, that is work output from the turbine minus the work in to the pump P. So, thus it is work out from the turbine is m.7 into H6 minus H7 plus m.8 H6 minus H8. So, work done by the pump, work input to the pump is m.1 into W P1 dot means at the inlet what is the work done, work input to the pump. So, plus m.4 work done at the P2 inlet point. So, thus it is WP1 at the inlet is V1 into P2 minus P1 by efficiency of the pump. So, and WP2 at the inlet, that is V4 into P5 minus P4 by efficiency of the pump. So, thus H1 which is the enthalpy of the feed at 20 kilopascal, that is 251.42 kilojoule per kg, and velocity which is Vf at the, or sorry, not the velocity, that is volume per unit mass, V1 equal to Vf at the rate 20 kilopascal, that is at 20 kilopascal pressure is 0.001017 meter cube per kg. So, work input at the P1 is calculated to be 2.29 kilojoule per kg. H2, which is H1 plus work done at the P1 point for input side. So, and H2 is found out to be calculated to be 253.71 kilojoule per kg. Energy balance for the mixing chamber, which is calculated to M3 dot into H3 plus M2 dot into H2, which is M4 dot into H4, that is H4 is 491.81 kilojoule per kg. Now V for specific volume at the for the stream 4, so which will be Vf at the rate Hf equal to 491.81 kilojoule per kg will be 0.001058 meter cube per kg. Thus, work input at P2 for the inlet side, so 7.21 kilojoule per kg. So, finding the H8 from the turbine isentropic efficiency, that is P8 is 20 kilopascal, S8s is S6, which is H8s, and that is 2215.5 kilojoule per kg, and turbine efficiency H6 minus H8 divided by H6 minus H8s, which thus H8 is 2357.6 kilojoule per kg. So, thus net work done, that is W net dot is 8603 kilowatt. Now, thermodynamic analysis with the innovative technology integration is the problem definition. When it comes to creating fuels and the chemicals through gasification, that is coal gasification or the biomass, a major challenge is the resulting gas law, gas low hydrogen to carbon monoxide molar ratio, and this ratio often does not meet the specific requirements for Fischer-Tropsch or the DME synthesis, even though it can vary based on the type of the feed used. One way to address this imbalance is using the water gas shift reactor to upgrade the gas. However, while this can be effective, it reduces carbon efficiency across the entire plant, which increases the carbon dioxide emission and raises the capital and processing expenses. Alternative methods like steam methane reforming provide hydrogen rich syngas, but they come with their own challenges. For example, steam methane reforming is highly endothermic and can lead to carbon dioxide emissions due to the combustion of the natural gas or for heat. So, thermodynamic analysis with innovative technology integration. Here the two figures are shown with the co-current configuration and the counter current configurations. Here the innovative technology integration, here the integrated systems which uses the gasifier. From the gasifier the syngas is produced, and that is combined with the that is a tubes with the catalyst, that is a reactor. So, thus here the syngas provides the or used as the feed to this reactor, and here we can get the that is hydrogen rich syngas and cooled syngas. That is depending on the requirement, we can maintain this catalyst type and the temperature in the reactor. And in the counter current, here we are using also syngas from the gasifier, and here we can see that natural gas and the steam here also supplied to this, and here we are getting the output the top at the top hydrogen rich syngas we are getting, where in the co-current we are getting the hydrogen rich syngas at the bottom, and here the in the co-current it was the hydrogen natural gas steam was fed from the top also along with the syngas, but here in the counter current syngas and the natural gas and steam are flowing in the opposite direction. So, this proposed concept for the integrating radiant syngas cooler of an entrant bed gasifier with steam methane reformer is shown here. Thermodynamic analysis with innovative technology integration, that is here it is shown that radiant cooler and then the that is steam gas reformer, where we are getting the natural gas and the syngas combined, and catalyst also used, that is spherical catalyst, which helps in the conduction, radiation, and also through which the diffusion also takes place, and conduction takes place through the wall, and the natural gas steam is supplied from the bottom. So, output will be natural gas and the syngas. So, that is a coal gasifier. Here in the second diagram, right side diagram, we can see that here the coal gasifier, that is from that we are getting the we are supplying the oxygen and the coal slurry from the top, and which will be gasified. Then the here the at the bottom it is natural gas and the steam are supplied. So, on the side we are collecting the coal syngas, and from the top we are getting the natural gas syngas, combined natural gas and syngas, that is the hot syngas we are getting. Thermodynamic analysis with innovative technology integration, that is biomass, natural gas and the nuclear to liquid fuels and the power process structures. So, this is the combined biomass is there, natural gas is there, and also the nuclear energy also here combined. So, here finally, where the hot or the syngas and the cool, pure clean syngas will be obtained. Again, integrating the reduced order steady state model. So, with the models also all the technologies can be integrated, and from which one can have the idea how much net energy will be generated. Then finally, system efficiency can be calculated, that is energy efficiency, which will be energy of the fuel products from the systems divided by energy input to the systems. So, here the systems might produce a variety of the outputs, including the beneficial byproducts, clarify which outputs are deemed valuable or the useful, and then determine the what constituents the main inputs to the systems, and then identify the key or the significant forms of the energy involved. Here system efficiency. So, it is complicated, the just flow sheet is shown here. This is also a flow sheet for the system efficiency. Here energy efficiency of the systems we can calculate using hydrogen mass flow rate into low heating value for the hydrogen divided by coal mass flow rate into low heating value of the coal. Exergy efficiency we can calculate, that is for the systems hydrogen flow rate, mass flow rate into exergy of the hydrogen divided by mass flow rate of the coal into exergy of the coal. So, exergy of the coal means specific energy of the coal in kilojoule per kg, exergy of the hydrogen, that is specific exergy of the hydrogen in kilojoule per kg, lower heating value, that is in kilojoule per kg, mass flow rate or the flow rate of the coal in to the gasifier which is feed for the gasifier in kilojoule per kg per hour, and MH2 dot, that is hydrogen production rate in kg per hour. Okay, that's all. It is the material was given by the by the foreign expert, as he was ill, so he could not deliver. So, I just displayed all the that is PPTs, and as it is his material, I just overall just read it, and wherever possible I just told something. Otherwise this simulation part and the complicated flow sheets, as I am not aware of this, I could not explain this. Thank you. The problem 1 question is, particles having a size of 0.1 millimeter, sphericity of 0.86 and density of 1200 kg per meter cube are to be fluidized using air at 25 degree centigrade and 202.65 kilopascal absolute pressure. The void fraction at minimum fluidizing conditions is 0.43. The bed diameter is 0.6 meter and the bed conditions 350 kg per solids. So, calculate the minimum height of the fluidized bed. Second bit, calculate the pressure drop at minimum fluidizing conditions. Third bit, calculate the minimum velocity for fluidization. Fourth bit, using 4 times the minimum velocity, estimate the porosity of the bed. So, here particle size diameter is 0.1 into 10 to the power minus 3 meter, that is 1 millimeter. Density is 1200 kg per meter cube, sphericity 0.86, voidage 0.43, diameter of the bed 0.6 meter, data given, and air is at 25 degree centigrade, delta P 202.65 kilopascal and density 2.372 kg per meter cube. Viscosity 1.845 into 10 to the power minus 5 Pascal dot second. So, we need to calculate length of the bed or the height of the bed, fluidized bed, and pressure drop, and then the velocity for the fluidization, and voidage, and the velocity when it is 4 times the fluidization velocity. Here we can see the column is given here, where the L1 by Lm is 1 minus, that is length of 1 minus voidage of the bed divided by 1 minus epsilon 1, which is epsilon 1 is 0, because here we have not started supplied the fluid yet. So, here voidage for velocity for the solid will be ms by density, mass by density. So, it is volume for the solid will be 350 divided by 1200 kg per meter cube, mass by density. So, this is 0.2917 meter cube. Now, volume of the bed, which will be cross sectional area into length. So, this is, so it is volume is 0.2917, which is pi by 4 d square, that is 0.6 square into L1. So, from this we can get L1, which is 1.0317 meter. Now, after knowing the length, here we can calculate Lm from this expression, where voidage is for the bed is given 0.43. So, 1 minus epsilon m is 1 minus 0.43 and epsilon 1 is 0. So, it is denominator 1. Now, from this Lm we are getting, which is Lm is coming 1.81 meter. So, first bit calculate minimum height of the bed is over. Now, second bit, here the pressure drop divided by length of the bed is 1 minus epsilon m into density of the particle minus density of the fluid into G by Gc. So, here we can calculate delta P is 1.81 into 1 minus 0.43 into 1200 minus 2.372 into G is 9.81 and Gc is 1. So, thus we can get here the because delta P we are right side we are multiplying Lm. So, delta P finally we are getting 12.121 Pascal or sorry 12,121 Pascal or 12.12 kilopascal. Now, the third bit where the velocity for the minimum fluidization we can calculate using the equations which given in the Kuhn-Levenspiel book. So, we can calculate substituting it is all the data whatever we have, and here 150 into viscosity into velocity for the minimum fluidization which we will calculate. Now, the sphericity and the bed voidage are given. So, substituting all the data, it is on the first term it is denominator phi s 0.86 and dp 0.1 into 10 to the power minus 3 square dp square, and here the epsilon m is 0.43. So, thus first term is over, only V O m minimum fluidization velocity data is unknown which we will calculate. The second term also V O m, that is minimum fluidization velocity is data unknown. So, substituting all other data, so we can get the minimum fluidization velocity. So, which is so G 9.81 and rho P 1200, rho is 2.372, that is density of the gas. So, thus minimum fluidization velocity is calculated as 4.375 into 10 to the power minus 3 meter per second. Now, the second bit third bit is over. So, we can go to the fourth bit. When volume is velocity is 4 times the minimum fluidization velocity, that is substituting it is the expression for the that is minimum fluidization velocity where the equation is there from in the Kuhn-Levenspiel, and in the third bit we calculated the minimum fluidization velocity as 4.375 into 10 to the power minus 3 meter per second. So, for this step we can take this velocity as 4 times of this minimum fluidization velocity, which is coming 0.0175 meter per second. Now, substituting here in this expression where minimum fluidization velocity is there, we can substitute there this 4 times the minimum fluidization velocity, and here we keeping the as velocity will be more, naturally voidage will be increase. So, voidage how much it will the bed voidage, that we can calculate as velocity is known, we can keep this bed voidage as unknown, and from this substituting the velocity, viscosity, because fluid is same, sphericity of the solid particle same, diameter of the particle same, only with the velocity voidage is changing. So, substituting all the data here in this expression we can get the voidage as follows. So, now calculating. So, here So, this is right side remaining also same, that is G into rho p minus rho 9.81 into 1200 minus 2.372. So, thus here only velocity value changed in comparison with the previous step. So, now we can get the bed voidage. So, bed voidage is coming as 0.60498 or 0.605 we can approximate. So, this is the bed voidage when the velocity is increasing and it is 4 times the minimum fluidization velocity, where it was 0.43 corresponding to the minimum fluidization velocity, and it is 0.605. So, another problem, that is the second problem. To clean and the a sand filter, it is fluidized at minimum conditions using water at 24 degree centigrade. The round sand particles have a density of 2550 kg per meter cube and an average size of 0.4 millimeter. The sand has the properties given in this table. So, bed diameter is 0.4 meter and the desired height of the bed at minimum fluidization condition is 1.75 meter. Calculate the amount of the solid needed. Second bit, calculate the pressure drop at these conditions and the minimum fluidization velocity, and using 4 times the minimum fluidization velocity, estimate the porosity of the porosity and the height of the expanded bed. So, thus here data is taken from the table, and that is round sand is there. So, for which diameter is 0.4 into 10 to the power minus 3, bed void is 0.42, diameter of the bed is 0.4, length of the bed is 1.75, water is at 25 degree centigrade, for which viscosity and densities are as follows: 0.9142 into 10 to the power minus 3 kg per meter second, density 997.31 kg per meter cube. And we need to calculate MS, mass of the solid, and which is volume into the density of the particles into the bed means 1 minus bed voidage. So, thus we can get the mass of the solid, because area is pi by 4 d square cross sectional area of the bed. So, it is pi by 4 0.4 to the power 2 and here length of the bed is 1.75 and area is pi by 25, 1 minus here the 0.42 is the viscosity, density is 2550. Thus, this is coming 325.25 kg of the mass solid. That is first bit is over. Second is pressure drop and the minimum fluidization velocity. So, again delta p by Lm is 1 minus epsilon m into rho p minus rho into g by gc. So, thus here pressure drop you can calculate, substitute bed voidage and densities are known. So, length of the bed also known. So, substituting all the data we can calculate the pressure drop, which is coming as 15,460.37 Pascal or 15.5 kilopascal. Now, the minimum fluidization velocity, which can be calculated using the equations given in the Kuhn-Levenspiel book, which is as follows. So, here using the data, that is porosity, viscosity and the sphericity as round spherical particle is taken. So, sphericity will be 1 and all other data, particle size are known, here the densities are known. So, substituting all the data we can calculate. So, from the data table, although it is nearly round sphericity, here from the data table it is given 0.86. So, we are taking 0.86 sphericity and calculating the velocity is coming right side is 9.81 into rho p 2550 minus rho 997.31. So velocity, minimum fluidization velocity is coming as 1.658 into 10 to the power minus 3 meter per second. Now third bit, porosity and the length of the bed is required when the velocity is 4 times the minimum fluidization velocity. So using the same equation expression for the minimum fluidization velocity, where the velocity, minimum fluidization velocity, we can substitute by 4 times the minimum fluidization velocity, and from which we can calculate the porosity data, because with increased velocity porosity increases, porosity changes when the velocity changes. So substituting the V, which is 4 times the minimum fluidization velocity, it is coming 6.632 into 10 to the power minus 3 meter per second. Now substituting all these data, we can get the in this equation we can get the porosity. So porosity is coming as 0.6. So we saw that porosity is changed, it is increased. Now the length of the bed we can calculate, which is using this expression L1 by L2 is 1 minus epsilon 2 by 1 minus epsilon 1, that is porosity is, will be different in the different heights. And so thus if you take L1 as the Lm is 1.75 meter, which is given. Now the epsilon m will be equal to epsilon 1 will be 0.42, that is at the initial conditions it is the corresponding to porosity of the 0.42, our length of the or the height of the bed was 1.75 meter. Now porosity is changed to 0.6. So corresponding to this, the length of the bed can be calculated using this equation, which is coming as 2.5375 meter. So length of the bed corresponding to porosity of the 0.6 is coming 2.5375 meter. Now coming to the fourth bit, sorry, with this the third bit it is over. So now we can solve another problem. A powder of mean size 6 micrometer and particle density 800 kg per meter cube, 1800 kg per meter cube is fluidized by air of density 1.2 kg per meter cube and viscosity 1.84 into 10 to the power minus 5 Pascal second in a circular vessel of diameter 0.5 meter. The mass of the powder charged to the bed is 240 kg and the volume flow rate of air to the bed is 140 meter cube per hour. It is known that the average and the bed voidage at incipient fluidization is 0.45 and correlations reveals that average bubble rise velocity under the conditions is 0.8 meter per second. Estimate the minimum fluidization velocity, the bed height at incipient fluidization, the bubble fraction, the bed height and the mean bed voidage. So now we can solve this tutorial, solve this problem under this tutorial. Data given, d particle size is the 60 into 10 to the power minus 6 meter, density of the particle 1800 kg per meter cube, density of the air 1.2 kg per meter cube, viscosity of the air 1.84 into 10 to the power minus 5 Pascal second, diameter of the particle is diameter of the column 0.5 meter, mass of the solid is 240 kg, that is it is volumetric flow rate is 140 meter cube per hour. So, again voidage at the incipient fluidization is 0.45, and thus here it is velocity, bubble velocity is 0.8 meter per second, and the bed voidage is given. So, volumetric flow rate is velocity into cross sectional area. So, here the average velocity, which is volumetric flow rate by area. So, we can get that as 140, as volumetric flow rate is given 140 meter cube per hour, and area which will be, so if you convert this, that is 140 meter cube per hour, and converting hour to second, we can divide by 3600. So, it will be meter cube per second, and here the calculating the V0 is coming 19806 meter per second, and here, so minimum fluidization velocity we can calculate, which is 33 dp mu by rho divided to the power minus 0.1. So, thus here we can get minimum bubbling velocity, you can say. So, here it is substituting the data 5.999 into 10 to the power minus it is 6, nearly 6 into 10 to the power minus 3 meter per second. So, velocity, bubble velocity we got. Now, we can get V0, as you found that V0 is means velocity, fluidization velocity is greater than bubbling velocity. We can say that it is the bubbling bed, means more bubbles will be forming, and thus here we can calculate the minimum fluidization velocity corresponding to this porosity of the 0.45. Now, similar to the first two examples, here substituting all the data, and if you, as sphericity is not given, assuming that completely spherical particles, so we can take the sphericity as 1, and thus substituting all the data, we can get the minimum fluidization velocity. This is coming 9.81, means right side is 9.81 into 1800 minus 1.2. So, thus minimum fluidization velocity is 3.81 into 10 to the power minus 3 meter per second. Now, the second bit, here we can calculate the length of the bed, and here the mass flow rate already known 140 it is given, and 240 it is given. Now, L1 into, so substituting and the A as cross sectional area. So here we can get from the mass flow rate corresponding to the bed voidage of the point 42. It was if you take completely static conditions, bed voidage will be there 0. So, corresponding to that length is coming 0.67906. During the fluidization, bed porosity is there, but in the static condition that is porosity is 0. So, now that we can take as the length L1, length of the bed. So, during fluidization we can take length of the bed as the L2. So, where the porosity is 0.45. So, corresponding to 0.45 we can get the length of the bed as the 1.2347. Now, third bit we can calculate the velocity. Third bit is the bubble height, bubble fraction. So, here we know that the volume which is 0.19806 and the fraction of the bubble into bubble velocity, given bubble velocity is given 0.8 and here 1 minus FB, that is fraction of the bubble, so which is unknown, and minimum fluidization velocity. So, substituting here the bubble volume and this fraction of the bubble in the bed is coming 0.244. Now, length of the bed corresponding to at these bubbling conditions, and Lm is the bed height. So, here Lm 1.23, which is L into 1 minus 0.244. So, thus length of the bed we can calculate corresponding to this in bubbling fluidization is 1.63 meter. Because corresponding fraction of some bubble also occupying the space in the bed. So, it is subtracting that we can get the bed height. Now, here the mean bed voidage will be calculated as here mass of the solid is length into volume of the bed into 1 minus F porosity into density of the particles. So, substituting this we can get the porosity, that is here volume length into area, volume of the bed is giving, and particle density is known. So, mass rate is also known. So, voidage is 0.583 coming, or the porosity is 0.583 it is coming. So, this is a few examples towards the tutorial classes on the fluidization technology, that is the fundamentals, where we calculated the minimum fluidization velocity and the if you substitute the fluidization velocity 4 times or the sometimes n times the minimum fluidization velocity, how the porosity changes, how the bed height changes, those things we calculated, and also the whether the bubbling what is the bubbling velocity, and if the type of the fluidization changing from the incipient fluidization to that is bubbling fluidization, how the porosity also changing, height changing, those things we just had the so we solved and we calculated. So, I hope this might have given some information or some knowledge how to design the fluidized bed that is equipment for the reaction, gasification, combustion or any purpose, because these are the fundamental things we should know, that is minimum fluidization velocity to maintain the fluidization, and the bed porosity, and also the bed height. Accordingly, height and diameter of the fluidization unit can be decided, and accordingly it can be fabricated. Thank you.